I go to this, and it's working. This whole inside. Okay. Okay. Let's get started. So, quick review. So we were going over one of the. Okay. Right. Oh, I want to maybe let's go a little larger. Okay. Yeah, we go to this application of entanglement, and we see that we can do super dense coding, where we send 1 qubit, and that allows us to send 2 classical bits. So there are 2 classical bits. Alice wants to send to Bob 0100 011 and Alice can do this by sending 1 qubit, and while also consume a shared entangled state. So the protocol is pretty funny. And yeah. So what they do is they start with the shared entangled state and depend on those 4 different things, and Alice will apply 4 different things to her part of the shared entangled state. So she either apply Z or apply X or apply XZ, and then she just sends this part of the shared entangled state to Bob. And then it turns out that those 4 operations will turn this shared entangled state. So the shared entangled state is being 00 plus 11. And if we do 4 different things on the A part of this state will turn into 4 different states that are actually also normal to each other. And they are called Bill bases, so they have those names. And yeah, so you have those 4 Bill bases, and they are also normal to each other. So you can measure in their bases and perfectly distinguish them. Okay. So that's super dense coding. And now, okay, so for now, any question? Okay. Now, then let's go to another protocol. It's like a reversal of super dense coding, and yeah, it's teleportation. So that's this is where Alice wants to send 1 qubit of an unknown state to Bob, and she sends 2 classical bits to do this. Okay. And as you said, we have unknown quantum state, and it seems pretty hard to send because we only have 1 copy here. So arbitrary unknown state can be A0 plus B1. So to learn AB, you need many copies of psi. And if you want to send AB, then you need some precision, so you need many bits. So, so how do you send just 2 bits and perfectly send this side to Bob? And this is where we use entanglement to do this really interesting thing. Okay. So at a very high level, as we said, Alice will have this unknown state. So let's first see a setting. So Alice will hold 2 qubits at the start of the protocol. She'll say hold a qubit, we call it A1. That's the unknown state she wants to send. So no one knows what this state is. It's alpha 0 plus beta 1. And then Alice and Bob share the entangled state as we said. So this shared entangled state beta 00 is the 00 plus 11 normalized. And so at high level, okay, so we have a 4-step protocol here, and but on high level, the first few steps is Alice wants to measure her 2 qubits in Bell bases. So Bell bases, as we just said, are those 4 different things. And yeah, so she has 2 qubits. She can measure in Bell bases. And but I guess as a practice, we will show that in detail. Okay. So she wants to measure in Bell bases, but so what you can do is kind of what we do at the start of the chapter. If you want to do Bell bases, then she want to turn the okay. So the Bell bases okay. build basis are the 4 state, right? So if you want to turn the build basis into computational basis, then measure in computational basis state. So there are beta 00, beta 01, beta 10, and beta 11, those 4 build basis state. And so if you want to do some inventory and turn those into computational basis state, 00, 01, 10, 11, okay? And so this is state and this is state. And this U actually equal to 2 things. So Hedema tensor I and C naught, which we are just going to say, okay? Okay, so we are going to do two unitary to turn the build basis into computational basis, then do computational basis measurement. And after that, we will send the measurement result to Bob, and Bob can do something to get this state back. Okay, so that's a high-level overview. But okay, so now let's go into the detail of the calculation. Okay. Detail of the calculation. So let's write down all the quantum state shared by everyone at every step of the protocol. So we have step 0, starting state. What are we starting with? We are starting with psi tensor beta 00. So those 2 qubits is in beta 00, and this state, as we say, is in unknown state side. So it's alpha 0 plus beta 1, and tensor this beta 00 is 1 over square root 2 0 plus 2 2. And okay, so for the ease of calculation, we expand this into summation of computational basis on all 3 qubits, because we are going to do calculation, a lot of more calculation later. Okay, so we expand into computational basis, then it's just a linear rule. So we have multiplication distributive, and so you have alpha 0 0 0, then alpha 0 1 1, then beta 1 0 0, then beta 1 1 1. Okay, and so nothing really happened, and square root 2 outside square root 2. Okay, so that's the starting state. And we write it as a linear computational basis because it's easier to see how each gate is applied on the computational basis states. Okay, and then we start doing our build basis measurement. It's a 3-step, because first we want to do C naught. So what is C naught? C naught, you might already heard about it. It's actually a classical gate. Okay, and it's a control knot. But first we give, we give a quantum definition. So it's a 2-qubit gate that, it's an actual 2-qubit gate, and 2-qubit is 4 dimension. So you can write it in this 4x4 matrix. Okay, so here we have definition, but it's easier to memorize it as the classical interpretation of it. Okay, so it's a controlled NOT gate. Okay, and NOT gate is also a gate. So what does it do? Basically, it's so it has a very classical definition on computational basis. Qubit. Okay, it has a very classical definition on control qubit. So it looks at some state A, B, right? And it says, so on computational basis state, so C naught on AB equal to, we'll see this more later. C naught on AB, so it's control, and the first qubit is control bit, and the second qubit is target. Maybe here, target. And what happens is if A is just, so you do nothing, if A equal to 0, and you do not on B, so I tensor X on AB if, or maybe I write this way. So okay, so the A part you never do anything, and you have A tensor not on B. Remember, X gate is not gate because it flips between 0 and 1 if A equal to 1. And yeah, so this is exactly what you see here. So this 4x4 matrix, you see a lot of 0. And it basically just say if you see the first qubit is 0, then you apply identity matrix on the second qubit. And the first qubit is 1, then you apply X gate on the second qubit. So basically you flip the B to negative B. Okay. So that's a CNOT gate. It's a HO2 qubit gate. You must describe it as some 2 qubit thing. But you see that you can easily see what they do on computational basis. So now we're starting state with these four things, and you can think about how CNOT apply on it. And yeah, so anyone want to answer? So CNOT apply on this 0, 0 part. What the result it is? The answer was CNOT apply on 0, 0. Okay, first is target, first is control, second is target. Okay. Yeah, and yeah, so CNOT on 0, 0, because the first the control qubit is 0, then it do nothing to the. Okay, so maybe let's go this easier to see. Put everything on same page. Yeah, CNOT on 0, 0. Then because the first qubit is 0, then you do nothing on the second qubit. Yeah, so you got 0, 0 back. Then CNOT 0, 1 is the same thing. So then yeah, it's still 0, 1. Then on those 1, 0 and the 1, 1, because the first qubit is 1, then you want to flip the second qubit. So 1, 0 become 1, 1, and 1, 1 become 1, 0. Okay. So that's what happened. That's your state after you apply the CNOT. Okay? So it's a 2 qubit gate. And okay, and then we say, oh, actually, I'm not sure I do the correct headma. Which headma? Okay, yeah, okay, correct. Yeah, and then we do CNOT, then we do headma gate on the first qubit. And remember, headma gate return all the matrix is this 1 over square root 2, 1, 1, 1 minus 1. And but another good thing to remember is the flip between 0, 1, and the plus minus. So headma applied on 0 will become the plus state, which is equal to 1 over square root 2, 0 plus 1, and headma on 1 become 1 over square root 2, 0 minus 1. Okay, and so yeah, so this is just brute force calculation, not too interesting. So there are 4 terms, and each headma will give you one. Put the 1 turn to 2 turns, you got 8 turns in the end. So for example, it's alpha 0, 0, then the 0 get turned into plus, and the plus is 0 plus 1. So you got 0, 0, 0 plus 1, 0, 0, because 0 becomes 0 plus 1. And similarly, say this beta 1, 0, 0, then this 1 get turned into minus, and the minus is 0 minus 1. So you got a so you got 0, 1, 0, this is 0, minus, from this minus sign, the 1, 1, 0, the 1 is this 1, okay? And yeah, so 4 terms become 8 terms, they are all here. And your square root, 1 over square root 2 get multiplied by another 1 over square root 2 here, so you got 1 over 2, okay? And yeah. And but now we can group things together because we know we are going to do major amount on the first qubit. And okay, so I guess here we can be a little more careful, make sure we don't do anything wrong. So 0, 0 becomes 0 plus 1. Okay, so that's correct. And finally, is 1 becomes 0 minus 1. Okay, and 0, 1, 0, 1. Okay, so everything correct. We got these 8 terms. And we regroup them together because we want to measure the first 2 qubit. And we are going to measure first 2 qubits in computational basis, so we group together the first 2 qubits with the same computational basis. So with the 0, 0 turn, so we have a 0, 0 here, 0, 0 here, and it's alpha 0 plus beta 1 here. And for the 0, 1 turn, we have the 0, 1 here and the 0, 1 here. So that's alpha 1 plus beta 0. And 1, 0 turn, so 1, 0 here, 1, 0 here. That's alpha 0 plus minus beta 1. And finally, for the 1, 1 turn, 1, 1 turn, so 1, 1 here, 1, 1 here. That's alpha 1 plus minus beta 0. Okay. So those 4 different turns. Okay, and so that's what happens after you apply C-naught handmark. And finally, we say we major in computational basis. Okay. And excuse me. So Alice majored the first 2 qubits in computational basis. And computational basis, so the measurement operator are basically projectors onto the bit strings. So you have like the measurement operator are like the projector onto 0, 0, projector onto 0, 1, dot, dot, dot. Okay, and so obviously the first qubit will get projected into one of those 4, and then you have some subnormalized state on the third qubit. That's 1 over square root to either one of those 4. Okay. And so first you can see the measurement probability. So you calculate the known of the post-measurement state, and you see the 4 outcome actually have the same post-measurement probability. Because the post-measurement states are all 1 over square root 2 alpha something plus minus beta something. Right? And the coordinate is non-square, then it's 1 over square root 2 square plus alpha square plus beta square, right? And we know alpha 0 and beta 1 starting with normalized, so alpha square plus beta square equal to 1, so the probability is 1 over square root 2 square and it's 1 over 4. So each one of the measurement outcome has probability 1 over 4. And more interestingly, what's the post-measurement state? So you renormalize this 1 over 4. 1 over 4 away, and basically cancel all these 1 over 2. And so the post-measurement state, if you get this 0, 0 outcome, then the post-measurement state is this alpha 0 plus beta 1. So let's get smaller. Okay. Oh, no, too small. Sorry. Okay. Yeah. Yeah. Okay, it's about correct. Okay, yeah. So if you get 0, 0 outcome, then your post-measurement state is, well, the first 2 qubits get projected into 0, 0, and the second qubit is this alpha 0 plus beta 1. And here that you see that we got a very good result, because here we already succeed, right? This is the state we want to send, this is psi. Okay? We start with alpha 0 and beta plus beta 1 on the first qubit. Now is alpha 0 plus beta 1 on the third qubit. But remember, Bob is holding the third qubit. And so if the measurement result is 0, 0, then Bob already got this unknown quantum state on his side, without us ever knowing this alpha and beta. Okay, so this is pretty cool. But unfortunately, we are not done yet, because there might be other measurement outcome. So say if it's 0, 1 outcome, then Bob will be holding this alpha 1 plus beta 0. And similarly, if, what is going on? Yeah, similarly, if the measurement result is 1, 0, then Bob will hold this alpha 0 minus beta 1, and it's 1, 1, then Bob will hold the alpha 1 minus beta 0. Okay, and okay, so now the question is, what does Bob do, or Alice and Bob do? Bob might hold. So one of the outcomes, Bob is really nice, and there are 3 other outcomes that's not quite your alpha 0 plus beta 1. Okay? Yeah, so the state got turned into something else. What do we do? We just failed. So if okay, and it turns out that yeah, we didn't fail, because Alice knows which happened. So Alice Alice has this measurement outcome, right? So 0, 0, 0, 1, 1, 0, and 1, 1. And so obviously Alice can send the measurement outcome to Bob. So this is where the classical communication. Okay. So what we need 2 bits of classical communication is so this is where 2 bits of classical communication we use. Okay. And so Alice used those 2 bits of classical communication to send those 2 bits to Bob. And so if Bob receives 0, 0, they are very lucky and they know the teleportation already succeed. And but even if Bob receives anything else, the protocol still succeed because those 3 states has a very strong correlation to this alpha 0 plus beta 1 if you look carefully. Basically Bob can correct his state by looking at which bit got sent over. So say if Bob receives 0, 1, then he knows that his state is alpha 1 plus beta 0 with some unknown alpha and beta. But even without knowing alpha and beta, Bob can turn this state back to this alpha 0 plus beta 1 because he can just apply the S gate. If Bob applies S gate here, then this 1 gate turns to 0, 0 turns into 1. And so Bob's state just get corrected back into the unknown side, even without knowing alpha and beta. And similarly, if Bob received 1, 0, then he got alpha 0 minus beta 1 here. And if he applied the Z gate here, you see that this 0 gate doesn't get change anything, but this 1 will get a minus sign that cancel this minus sign. So once again, he can correct this alpha 0 minus beta 1 back to alpha 0 plus beta 1. And then similarly, you can check yourself. If Bob receives alpha 1 minus beta 0, he can apply X, then apply Z, and and once again he will get back into alpha 0 plus beta 1. So that completes the teleportation protocol. So send. So here the sender result is 2 bits. Okay. And probably the one. So we see that no matter what, so Alice has 1/4 probability to get any of the measurement outcome, and once she sends the 4 measurement outcome to Bob, then Bob knows which one of the 4 cases he's in. Then Bob can always correct the state back to the alpha 0 plus beta 1 that Alice wants to send to Bob. And here we have some notation things. So if you want to write the 4 different kind of correction in a succinct way, then we can say Bob apply Z to the M1 and X to the M2. And so basically this string we say is M1 and 2, so it means that if first qubit is 1, then Bob apply a Z here, and if second bit is 1, then Bob apply X here. So this is just a notation thing. But anyway, here is the teleportation protocol. Let's stop a little bit. Any question about what this protocol do? No? And this is called teleportation because it's kind of like it is teleport this unknown state to Bob. And I guess teleport means that the Alice side no longer has this thing. So this thing appear on the third qubit here, and Alice side no longer has this side here because you see the end of the result. Alice has one of the 4 computational base state, and Bob will hold the unknown state side once again. So that's teleport. Okay, and the teleport, I guess we'll say here. Okay. So interesting point. The teleportation seems very weird. So this kind of thing Yeah, this shows a bit of a weird behavior of quantum mechanics. So you see that we, because we think the measurement, when we do measurement, then the state got changed, got put, how should I say, got collapsed into something, right? And here we see a really interesting phenomenon is that its measurement collapses into something. It doesn't care about physical distance. Yeah, so Alice and Bob can be really far away. There is no physical restriction about how far away Alice and Bob is. And but we see that when Alice measures her side of the state, so they have this joint state, and Alice measures her part of the state. So Alice collects her part into 0, 0, 0, 1, 1, 0, and 1, 1. And Bob's side got correspondingly chosen into one of the four. And so if you think in physics terms, it's kind of weird because yeah, Alice and Bob can be really far away, and if you think about special relativity, it says that you cannot send information faster than speed of light. But if Alice and Bob are really far away, how can this change of information happen instantly? Throughout maybe what Alice and Bob is 100 light years away. So yeah, but this is still what we think happen quantum mechanically. So when you do measurement on some part of integral state, the other part get changed immediately. And this is where Einstein start complaining about quantum mechanics because he doesn't think this makes sense. This is supercreation at a distance. Yeah, but nowadays physicists just accept that this is happening. Okay, and but we need to address the complaint about we are sending information faster than speed of light. Okay. So actually, we don't have information faster than speed of light happening here. So this is something interesting that we'll see in more detail in the next part of today's class. Yeah. So why is there no faster than speed of light? So the thing is, Alice got the major outcome here, so 4 different major outcome here. But before Alice actually sent these 2 bits to Bob, Bob doesn't know which 4 of those. And actually Bob has no way to know which 4 of those he is holding. He has some uniform mixture of those 4, and basically from Bob's view, that's the same as he was holding this state. Okay, so we'll make this more formal on just the later part of today's class. Okay, yeah. So Bob doesn't know anything about psi. So Bob's side, although we know he is one of those 4 things that correspond to alpha and beta. Before Alice sending those 2 bits to Bob actually doesn't have a way to learn anything about alpha and beta. Okay, even though mathematically we say this multiplication and distance already happened. Okay, so yeah. So no actual faster than speed of light information transfer is happening. So special relativity is still safe. And okay, and now we think about more about how the information on the side is happening. And okay, so this part is some really interesting state. So we say that after Alice do a measurement, but before Alice send the information to Bob. So Bob doesn't know anything about psi, doesn't know anything about alpha and beta. But Alice doesn't know anything about alpha and beta either, because Alice only gets one of the 4, 0, 0, 0, 1, 1, 0, 1, 1. And those 4 bits are just drawn uniformly random. We say we'll recalculate. The probability is 1 over 4. That doesn't depend on anything on alpha and beta. So yeah, so this is the interesting in the middle of teleportation step, where no one knows anything about psi. Alice doesn't know psi, and Bob doesn't know psi at all. Okay? So yeah, this is something interesting that can happen in quantum information. You can kind of break the information into 2 parts, and none of them know anything about your state. But yeah, so none of them know anything about state, but once Alice sends the casting information to Bob, then Bob knows the state about. Bob knows a lot about psi, because Bob can, once again, Bob, as we say, can apply the correction on his part, depending on which of the 2 bits he received. and then he will get one copy of psi perfectly. Yeah. So yeah, that's kind of interesting what can happen in quantum information, where you can kind of break quantum information into two party, and we break the information about side into two party, and neither side know what is this side. Neither Alice nor Bob know anything about side, but once they combine their information, then they can recover side perfectly. And yeah, so if you study cryptography, then there are some protocol built on these interesting quantum phenomena like secret sharing, etc. That's out of the scope of this class. For now, we just know that we have this interesting effect now. Yeah. And yeah. And once again, this is why this is called teleportation. So the teleportation because it's like Alice is sending her part of the state to Bob. So her part. So she teleport the state to Bob, and her side of the copy is destroyed. And we know this must happening because there is no cloning theorem. So they cannot both hold the copy of side. So one of them holds this unknown copy, and the other one don't anymore. It's a teleportation. And yeah. So what's interesting the interesting thing here is they can do a teleportation by just sending classical information. Even though classical data cannot quite hold the quantum data, but they can still do this perfect teleportation by consuming one bit of entanglement between them. Okay, any question? Not. Oh, we're a bit slow. I guess it's okay. Okay. So let's talk a little more about this, then let's start a little bit about density matrix. And so we have a bit of a resource theory here. Is we can think about how we use our resource during the communication. So what are resources we use in communication? So basically, how many communication we do, and also we can view the shared entanglement as kind of resource in communication. So we can define this E bit as one pair of maximum entangled state shared between two party and its above. Here we just consider two party, and then we can kind of write down the equation of a protocol. So what the resources we use to get what kind of communication while we do the protocol. So we see that in super density coding, we consume one pair of entangled state, and we send 1 qubit, and the result is we send 2 qubit. And in teleportation, we send 2 qubit and we use one pair of entangled state, and we get 1 qubit. Okay. So we can see they are kind of symmetric. And so one of them use 1 qubit to send 2 classical bit, and the other one of them use 2 classical bit to send 1 qubit. And unfortunately, if you pair them together, then you are just wasting resource, because if you pair them together, then basically you are using 2 bits of entanglement to do nothing. Okay. So this thing's a little inefficient, but that's what our protocol do. And also we see that we can, at the very beginning, when we talk about maximum entangled state, we say that we can use 1 bit of quantum communication to create, because one copy can create a maximum entangled state, and send one of the bit to the other copy. So yeah. So here is a little bit about resource theory. And if no question, then let's try to start a little bit on density matrices. Okay, so what density matrix want to do? I guess a very good multiplication is here. We want to describe this kind of state. So maybe think about this kind of state of Bob state. So how do we describe a state that has like one variable probability of 4 different kind of state? Okay. So this is so in physics terms, this is what we call an ensemble. Okay. So this is an ensemble. We call the ensemble. So the ensemble okay. So this is a more general term. ensemble means like probability mixture of something. And here we are talking about probability mixture of quantum states, so it's an ensemble of quantum states. Okay. So obviously you can describe it in this way. So you have this state with 1/4 probability, this state with 1/4 probability, and etc. So you can just write down. So you can describe your ensemble with so like a pair, set or pair of probability and state. Okay. So that's one way to describe it, but there is a better way to describe it. Okay. So here is the example of ensemble, and maybe we give another example. So let's say, so this example we see like before. And so this is what happens when you do, say you start with some plus state and you do a computational basis measurement. And as we say, you will get 50% 0 and 50% 1. And they want to kind of describe this kind of state, this kind of ensemble. Do we have like a more succinct way to describe this thing? And the answer is yes. But first, I want to stress that there is a difference between this classical probability mixture and quantum superposition. Okay? So 52% 0 and 50% 1 is different from a superposition between 0 and 1, any kind of superposition. So for example, like equal superposition of 0 and 1 will be this 1 by square root of 0, 1, it's the plus state. And yeah, so this 50% 0, 50% 1 is nothing as the superposition 0 and 1, basically the plus state. And anyone want to answer why? How do you do something to distinguish this mixture and this thing? Okay. And yeah, and well, a way to distinguish the mixture and this thing is you do a X basis measurement. So as we know, the plus state is the eigenstate for X basis for the X operator. So if you do X basis measurement, it will always give you a +1 outcome. But when you do X basis measurement on either 0 or 1, you get 50-50 probability. So this is what we say in the Stenger experiment, right? And yeah, so you see that, and yeah, so if you do X basis measurement, then you get -1 +1 with a uniform probability on either of these. So in particular, you can get -1 outcome on measuring this, but you cannot get -1 outcome measuring this. So this ensemble is different from the starting state, that's the superposition of them. So classical mixture is different from quantum superposition, that's something. And yeah, so maybe let's change the color. So this is different from quantum superposition. So something to remember. And anyway, let's go to actual the density matrix part, as we said. We want to get a more succinct mathematical form to describe this thing. And we started with kind of a derivation. Okay? It's not quite a derivation, but I think it's part of intuition. So yeah, so we have some in classical mixture of quantum state, and let's see we are just mixing two of them. So psi 1 with probability P1 and psi 2 with probability B2. And we want to measure something physical on them. So how about we measure expectation value of some operator A? And as we know, the expectation value of some operator A, well, with what some state is this kind of inner product of the symmetry in the operator between your states. So if the state is psi 1, then the expectation value is this A symmetry with psi 1, and similarly psi 2, then it's this expression. And well, they have probability mixture P1 and P2. And so when you do expectation value, you should average according to P1 and P2. So the expectation value should be this. Okay. And then, okay, so next line we do nothing. But then we do cyclic permutation. Yeah, why do I even write this line? Yeah. And And the next line we use a cyclic property of the trace. So you can prove this. Also pretty easy that trace AB equal to trace BA for any matrix A and B. And so now we can view this trace. Okay, so we are actually doing something, sorry, I forgot. Yeah, so here is this, and next line, we do something seems trivial. Okay. So we know this inner product is a number, right? The 12 is a number, and but the number we can view it as a 1x1 matrix. So we can write a trace here and basically do nothing because it's a 1x1 matrix. Okay. And then we do something funny. Then we know that yeah, it's a 1x1 matrix, but it comes from a row vector times a matrix times a column vector. Okay. And trace has this cyclic property, so for any matrix AB of any dimension, trace AB equal to trace BA. And so what we can do is we can view this psi1 as A and this A times, so psi1 brought as A is A psi1 as B. And so we reverse the order of AB, so we basically move this psi1 to the end. And this becomes trace A times psi1 cat, then times psi1 bra. And so the matrix like this, and we have a matrix, then have this. Okay. But we move this one to here, right? So we have now A and psi1, like this. Okay. And now we see that after we do this funny operation, then the trace is not doing nothing anymore because now we actually have like n by n matrix if n is the dimension of the Hilbert space. Yeah. And yeah, so we do this cyclic thing, then we're actually tracing onto some actual matrices. And similarly on the psi2 part, we do a similar thing. And then we can do linearity with this whole bunch of trace. We can move the P1 and P2 inside with this project onto psi1 and project onto psi2. And then we see that both sides is A, so we can take out the A. So we're actually we're calculating trace of A and this part, which is another matrix, another n by n matrix. That's P1 times project of psi1 plus P2 project of psi2. And so this thing is a density matrix because you will see that when we want to calculate the expectation value of A, we just need to know this thing. Okay, so this is a density matrix. We usually call it rho. And so we find out that yeah, so expectation value of any operator A is just determined by this thing that doesn't depend on A. This just depends on your parameter of your ensemble, right? So it depends on P1 psi1 and P2 psi2. So we found out that if we know this weird matrix P1 times projected psi1 plus P2 times projected psi2, then we can calculate expectation value. And actually, this matrix is very powerful. You can calculate everything about this ensemble from just knowing this matrix. And yeah. But so now we gave a definition, and we'll prove that this actually give you everything later. Is a very strong description of quantum system. Actually describe every information. But for now, we have this ensemble interpretation. So we have some ensemble of quantum state. So describing some pi psi pairs. Okay, pairs. And so we have those pi psi. Then we can always define this matrix, right, by just doing calculation. Is a summation over I, then pi times the projector onto psi. And yeah, so this is the definition, and we will show later part of this section that this totally describes the system, and this matrix rho is called a density matrix. Okay. Any question about the definition of a density matrix for now? No. And yeah, as we said, ensemble is just probability mixture of something, and then here the things are the quantum state. Okay. And okay, so we need to check a lot of things on this row. I have 2 minutes, so I guess let's show really quickly and let's go more carefully next time. So we say rho is a total, rho totally describe the system. And for now, we are thinking rho is representing this ensemble. So we want to show that rho has all the information about the ensemble. Okay, and so let's first check different things. So first we want to check. So I guess there are 2 things we want to check. First is rho can also describe how this ensemble will evolve by some unitary, and another thing to check is measurement. And skip the derivation. Basically, we think about the system can evolve through some unitary. So then if system got applied by some unitary, then psi will get to u psi. And then rho will get evolved to u rho u dagger. Yeah. And so if you just go the result, then this is what will happen, and this will correspond to how evolved ensemble. Okay. So the u rho u dagger will corresponding to this ensemble where every cycle evolved by this u. And also measurement, then we can check that. Okay, so there's quite a bit of calculation, and but you can check that when you do a set of generalized measurement n on your ensemble psi, and then you can calculate the probability of getting measurement outcome m is this thing. So this is trace. Okay, so maybe let's highlight too. So probability of getting US outcome is this trace and dagger and rho, and the post measurement outcome is this thing. Okay. And rho and dagger trace over and normalized by this. Okay. And yeah. So I guess here we can think, okay, we don't have, we're almost over time, but I guess I can write down one equation. So we can have the, well, basically, you can basically memorize this by the post measurement state. So kind of like this thing, right? So rho get turned evaluated by unitary, rho get u rho u dagger. And the post measurement state, when you have psi, it becomes m psi. And so post measurement state or post measurement density matrix is m rho and dagger. About this thing. And so the probability of this thing is a trace of it. So this is a cyclic of this. So this is also equal to trace and rho and dagger because of the cyclic property. And yeah, and you see the post measurement state this thing and normalized by its probability. Oh, sorry, we'll go over time too much, but yeah. So that's a quick introduction to density matrix. And any problem? If there's no problem, then hopefully we can have class on Thursday. So as there is a typhoon coming, but yeah, we'll see whether we will class on Thursday. Yeah. Okay, so see you next time.